Hello everyone and welcome to the channel. In this video we'll continue taking a look at our clock circuits and specifically make sure that we can switch between our clocks in a safe way for the CPU. I hope you enjoy! Okay, so in the past few videos we've been building this clock. We have three different clocks. The first one is the pulse clock, which is just a debounce button. The second one is the slow clock, which runs at visible speeds, so you can see what's happening with the CPU, and then a fast clock, which can go up to 10 MHz in order to run the CPU as fast as possible. And we are switching between these three clocks using a multiplexer, the 74HC253, which then outputs into a flip-flop, which gets us both the clock and the inverted clock, as well as a division by 2 and a clean 50-50 duty cycle on the output clock. So this works well. In this video, I want to discuss how we can do safe clock switching. This means that we need to find a way to switch between our three clocks at a point in time that doesn't cause issues with the running programs. So if you were to switch in the middle of a cycle, you risk crashing the CPU because the clock signal is glitchy or doesn't look right if you don't do it properly. So let's get to it. The first thing I want to do is to rethink the way we output the clock, because right now the multiplexer is switching between intermediate clocks and it makes it harder to reason about when to switch the clock signals. So what I want to do is to move this flip-flop before the multiplexer so that the multiplexer only sees the final clocks. So I'm going to move this one here, and then we have a spare flip-flop that we can use for the slow clock. And the pulse clock doesn't actually need a flip-flop. It's even better if it doesn't have it, because then the button pulse is directly the clock signal. If the button is not pressed, then it's a low phase of the clock. And if the button is pressed, it's a high phase of the clock. So I think it works better this way. Now, you'll notice that we don't have a way to output the inverted clock anymore, because that was a property of our flip-flop. However, we can replace our multiplexer and use a 74LS251, which is a 3-bit multiplexer, so it has 8 inputs, but it also has normal and an inverted output. So this is good. Now we could definitely use this one. The only thing is it has a output enable input, and we probably don't want to ever tree-state the clock. So this we don't actually need, but if we go down to the 151, the output enable turns it into an enable signal. And so the way the enable signal works is if it's taken high, then the clock is forced low. So we're going to be able to use this in order to stop the clock when we use the halt line. So this is going to be useful later. So I'm going to go to the 151. So let's wire it up. So for now, I'm going to tie the enable signal low, and the third input bit I'm going to tie high, which means that we have to wire our input clocks like this. There we go. Now let's wire up the clocks. There we go. Now the question becomes, when can we switch between the fast and slow clock? And when can we switch between the pulse and the run clock? But let's talk about the former. When can we switch between the fast and the slow clock? Let's look at the signals first. So let's say that this is the slow clock and that this is the fast clock. Now the slow clock is going to look like this. And the fast clock is going to be orders of magnitude faster. I'm going to draw it like this. It's really much, much faster. So when is it safe to switch between the two? What we want to do is to switch when both are in the same state. Let's say we want to switch when the slow clock is low. We also have to switch when the fast clock is low. This way the switch is not noticeable. And what we can do, because we have edge triggered circuits, is we can switch when we are on a low slow clock and when we are on a falling edge of the fast clock. So if we zoom in to the fast clock, so during this whole interval, the slow clock is going to be 0. If we switch clocks here, during this falling edge, then it makes sense because we do not shorten the length of the fast clock cycle. If maybe this is the fastest clock the CPU can take, we don't really want to shorten it. So we have to switch at the beginning of the fast clock cycle here. Now we can use the same strategy to switch from the fast clock to the slow clock, because if we zoom in on the slow clock, so let's say that this is the falling edge of the slow clock, and after some time it goes up again. We're going to have so many oscillations of the fast clock around this that we can switch at the same place in the slow clock. So basically the way that this is going to work is we're going to have a button press, then a low going edge of the slow clock, and then we're going to have a low going edge of the fast clock, and this is going to switch the mode. And this way we are guaranteed that we never shorten the fast clock cycle, which is really important. So let's see how it looks like in the circuit. So in order to do this, we're going to need a negative edge triggered flip-flop. So I'm going to use the 74HC112. So the way these work is they're going to transfer what's on the J and K inputs to the outputs on the negative edge of the clock input. And so you have to give them inverted inputs in order for those inputs to translate to the output. So we're going to need 2 of them. So they need a power supply and a decoupling capacitor. We're going to take the positive input here and the negative input here and input it like that. And then we're going to chain this into the second one the same way. And then the final output is going to be our chosen mode. Now we want the first JK flip-flop to toggle on the slow clock. And we want the second JK flip-flop to toggle on the fast clock. And we're going to tie the set and reset high. So now the way this is going to work is when we're going to press the speed button, so on the rising edge of the signal, which is basically the pressing of the button, the first flip-flop is going to toggle from low to high or from high to low. And then when the slow clock goes low, we're going to transfer the state to here. And then when the fast clock goes low, we're going to transfer the state to here. And so this makes sure that we're only going to switch clocks when both the slow clock and the fast clock are low. So let me move this here for now. Now we have to talk about when it is safe to switch between the pulse clock and the run clock. And so if we think about it, it's actually exactly the same thing as switching between the fast and the slow clock. There is one that is orders of magnitudes slower than the other, and that's the pulse clock. So this is the first one that we're going to put here. So depending on which clock is currently the run clock, this is the clock that the flip-flop needs to trigger on. So we're going to need to figure this out. Now, there is one issue with this. The GK flip-flop only triggers on a negative going edge, but it's completely possible that we are not going to press the button of the pulse clock when we want to change mode. And so this is not going to work. So we can just remove this one and say that if I'm not pressing the button, then I'm only concerned about when the run clock is going to go down. And if I'm pressing the pulse button, then the mode button is going to take precedence. And so if I press both of them, the clock is going to switch from high to low on the falling edge of the run clock. We actually now have a spare JK flip-flop, and it also needs a power supply and a decoupling capacitor. And I'm going to tie all the inputs high on the spare one. So this is how we switch between our three clocks. Now the only question that remains is how do we generate this run clock? It is the currently selected fast or slow clock. And for that we have to use another multiplexer. So we need to copy this circuit and remove the pulse and run input, which we can tie to ground. And then we just need to duplicate these inputs like this. And we have the run clock on the output. There we go. So let me make a bit of cleanup. Okay, so now we're able to switch between our two clocks in a clean way. Okay, so this is the breadboards where we left off the last time. I'm going to focus on the clock for now. So what we want to do is to re-implement those three chips. We need to replace the multiplexer, and the flip-flops have moved. So I'm going to redo this whole row. I'm just going to pull everything out for now. Okay, so I have here 274 HCT151, which I'm going to put at the end here. So they need power and ground and a decoupling capacitor. We need to connect pin 7 to ground on both of them. That's the enable pin. Then pin 5 on the right run is going to be the clock. And so I'm going to connect it to our reset circuit again. And I also need to put back the LED. I'm going to use pin 6, which is the inverted clock for now. The slow clock needs to come in on pin 4 and 3 of both of them. So that's pin number 3 of the 555 timer. Then the fast clock needs to come in on pin 1 and 2. There we go, and then the pulse clock needs to come in on pin 12 to 15 of the second chip. Okay, now the slow clock needs to go to pin 15 and 14 of the first chip here. And the fast clock needs to go to pin 12 and 13. Okay. So this should be all the clocks. Now we need to wire up the selection bits. And so these are going to come from the 74 HCT 112. So I'm going to add them here. So these need power and ground. And decoupling capacitors. We also need to connect pin 4, 10, 15, and 14 to VCC. Okay, so we need to connect pin 5 to pin 11 and pin 6 to pin 12. So for this one, pin 9 is going to be the fast and slow selection bit, and it needs to go to pin 10 of both multiplexers. So the input bits are coming from a D flip-flop, which needs power and ground, and a decoupling capacitor. So pin 2 is coming from pin 8. And pin 3 is coming from pin 9. Then on this one we need to connect pin 8 to pin 12, pin 10 and 13 to VCC. Finally, pin 11 is the speed button. And now we need to connect the clocks, and I actually made a mistake here. The clocks need to go through a flip-flop. I'm gonna add it here. It needs power and ground and a decoupling capacitor. And then we need to connect pin 1, 4, 10 and 13 to VCC. We need to connect pin 8 to pin 12 and pin 6 to pin 2. Then pin 11 is going to be the inputs of the fast clock, so that's this wire here, which I need to remove. Okay, so this is our fast clock. Pin 9 needs to go to pin 13 of the JK flip-flop. And then it also needs to go to the multiplexers. Okay, so this is the fast clock flip-flop. Then we also need to bring the slow clock flip-flop here. To pin number 3. And then pin 5 needs to go to pin 1 of the first JK flip-flop here. Then it also needs to continue to the multiplexers. Okay, so this is the clock flip-flops wired up. And I also think that is the fast-slow JK flip-flops completely wired up as well. So now we need to do the mode. So the mode button is going to come in here. Go here to pin number 3. Then we need to connect pin 2 and pin 6 together. Pin 1 and 4 need to go to VCC. Then pin 5 needs to go to pin 3 of the second JK flip-flop. And pin 6 needs to go to pin 2. Here we need to connect pin 15 and pin 4 to VCC, that's already done. Pin 5 is our pulse and run bit. And so this goes into pin 9 of the second multiplexer. And then pin 1 is the run clock, which is pin 5 of the first multiplexer. There we go. And so all the unused pins of this JK flip-flop needs to be connected to VCC. Okay, then on the first multiplexer we need to connect pin 11 to VCC and pin 9 to ground. And also on the second multiplexer, pin 11 to VCC. And I believe that's everything. So let me double check that I've got everything. I've tested it and it works. Not sure how well you can see this LED over here. But this is the slow clock. And then when I switch to the fast clock when it's low, you can see that it finishes the cycle before switching to the fast clock. And if I switch again, you can see that there's a delay. And then if I do the same thing to switch to the pulse clock, so when it's low, you can see that it finishes the cycle by going high one last time, and then it goes into the pulse clock, and the pulse clock also works. So let's fire up the oscilloscope and see if we can show this on the scope. So in yellow is going to be the speed button. And in blue, it's going to be the final clock. So I'm going to trigger on the button and do a single capture. Okay, so my signal is really noisy here, but you can see that as I press the button, it actually finishes the slow clock cycle. You can see it's symmetrical, and only after that it switches to the fast clock. So you can see that after that it switches to the fast clock. So this seems to work. Now let's see when we switch to the pulse clock. In yellow is going to be the pulse button. And then same thing in blue is going to be the final clock. Okay, so on this capture you can see it pretty well. As I press the button, it finishes the slow clock cycle before switching to the pulse clock and staying low. Okay, so this seems to work pretty well. Okay, so one thing I want to do is to be able to set which mode and which speed the clock puts on power up. So if I'm working on debugging some hardware, maybe I want to boot on the slow clock, but if I want to work on some software, then I want it to run as fast as possible each time. And so I wanted to boot on the fast clock. Yeah, so I want to be able to change this. So I'm gonna add a dip switch, and I want to use one of those single pole double throw dip switches. So the way it works is that when the dip switch is on, the left switch is connected, and when the dip switch is off, it's the right switch that is connected. So let's keep that in mind. So I'm gonna add a dip switch. And actually, you know what, I'm going to make a copy of this symbol to make the switching explicit. So let me do that now. Okay, so I think this kind of represents what it is doing. The bottom switch in this orientation is the one that is normally closed. So when you don't activate the dip switch, this is closed. And then when you turn on the dip switch, this is closed and then this is open. I guess that's my best try at making this a bit more explicit. Let's just roll with it. Okay, so we're going to have 4 signals here. So when the leftmost dip switch is on, we're going to be on the fast clock on reset. When it is off, we're going to be on the slow clock. When the rightmost dip switch is on, we're going to be on the pulse clock. And when it is off, we're going to be on the run clock. And so those signals need to go into the set and reset inputs of the flip-flops. When reset is low and I want to be on the pulse mode, I want to set those flip-flops here. So we're not going to connect them to VCC anymore. And the same thing goes for the run clock. And let's do the same here. When I want the fast clock, I want to set the flip-flops. And when I want the slow clock, I want to reset the flip-flops. Now, what goes into these signals? Well, we need to input the power up signal. And so this one is going to go to all of these. So now when the dip switch is connected, then the power up signal is going to go and either set or reset those flip-flops. The only thing we need is to add pull-ups here because one of those is not going to be connected, and so it would be a floating input on the flip-flops. So we need to add a few pull-up resistors. I'm going to take the same resistor network that we used for the counter. And on Breadboard, I'll probably use regular resistors. And this is going to VCC. The only thing we need to keep in mind here is because at all times, 2 of them will be connected. Then the strength of the pull-up is going to be divided by 2 because there's going to be 2 resistors in parallel to VCC. So the total resistance is going to be 5K, but I think this is fine. This page is getting a bit cramped. I want to do some cleanup, so I'm going to switch it to A3 so we have a bit more space. There we go. Let me do some cleanup so we can see a bit better everything. Okay, I think this way we can see things a bit better. So I just need to import the power up pin and connect it. And the reason that I'm not using the reset signal to do the power up on the clock is because the reset depends on the clock to function. So we need to go 1 level higher and use the power up signal to set up the clock. Okay, so off camera, I went ahead and added some labels to the clock so that we can see which button does what and what the LED mean. So let's go ahead and implement the dip switch. So I have here the single pole double throw dip switch I was talking about. I'm going to plug this here. We need to add 4 resistors to VCC. There we go. And then on the other side, we need to connect all the pins together. There we go. And then this signal comes from the power up signal. There we go. Okay, so then on the flip-flop, we need to disconnect pin 10 and pin 13, which are currently pulled up to VCC. And this is the fast on reset signal. Going to pin 10, Then it needs to go to pin 4 of the second flip-flop here. And to pin 10. So pin 4 and 10 we need to disconnect from VCC. No, actually, sorry, that's not the signal. That is the slow on reset. That needs to go to pin 13 of the first flip-flop, and then it goes to pin 15 and 14 of the second flip-flop here. There you go, so that's slow on reset. Now fast on reset needs to go to pin 10. There we go, and then to pin 10 of the other chip. And to pin 4. There we go, so that's the speed selection wired up. Next, the pulse on reset signal needs to go to pin 4 and pin 4 of both chips. There we go. And then the run on reset needs to go to pin 1 and pin 15. There we go. So this should be everything wired up. Now, if I plug in the power, I should be on the slow clock. And that's correct. If I switch the first dip switch, I should be on the fast clock. That's correct. And then if I turn on the last dip switch, I should be on the pulse clock. And that's also correct. And then if both are high, I'm also on the pulse clock. Yeah, that's great. All right, so in this video, we've added clean clock switching between our 3 clocks and a default setting for which clock to select when we power up the circuit. In the next video, we will go back to working on the CPU. And now that we have a clock and a reset signal, I think we're going to be able to start up the CPU and see it running. So I'm pretty excited about that. Anyway, I hope you enjoyed this video. Let me know in the comments if you've got any questions or feedback. And I hope to see you in the next one. Goodbye.